All right, let's jump right into this explainer and demystify virtual private networks, or VPNs. We're going from everyday internet analogies all the way down to advanced network engineering. So if you've ever wondered how your data actually travels across the web and how different tools protect it or completely fail to protect it, you are definitely in the right place.
To give you the full picture, we're taking a zoom-in approach today. We'll start with normal connections, dive into VPN tunnels, look at who exactly sees your data, check out the OSI layers under the hood, compare security layers, and finally, pinpoint exactly when you actually need a VPN.
Section 1. Normal connections. Let's establish the baseline data flow. Before we can really appreciate the heavy-duty protection a VPN offers, we gotta look at how your data normally travels. And it all kicks off with DNS, the domain name system. Think of DNS as the internet's phone book, right? When you call a friend, you don't memorize their actual number, you just tap their name in your contacts. DNS does the exact same thing for the web. It translates a human-readable name you remember, like google.com, into a machine-readable IP address. That IP acts just like a postal address, so your data packets know exactly where to be delivered.
So, here's how a standard connection actually plays out step by step. You type a URL into your browser, and your device asks your Internet Service Provider, or ISP, for directions. The ISP's DNS server looks up the IP address and sends it right back, so your device can connect to the destination. But here's the catch, and it's a big one. In a normal setup, those standard DNS queries are completely unencrypted. That means your ISP, or honestly anyone snooping around your network, sees exactly which websites you are asking to visit.
Moving right along to Section 2, VPN tunnels and encrypted data flow.
Now, dropping a VPN into the mix completely changes that flow. A normal connection, that's basically like sending an open postcard through the mail. Literally anyone handling it can read the address and your message. But a VPN is like taking that same postcard, sliding it into a locked, opaque envelope, and shipping it to a secure forwarding facility. All your ISP sees is that you're sending a locked envelope to a VPN server. They have no clue what the final destination is, and they can't see the contents. Plus, your real IP address is totally masked from the destination website, replaced entirely by the VPN server's IP.
Section 3. Who sees your data? Let's break down visibility.
This is absolutely crucial because a lot of people misunderstand exactly who can see what at each stage. Let's bust a major myth right now. A VPN does not make you a complete ghost online. Your ISP absolutely knows you're using a VPN, they just can't see what you're doing inside that encrypted tunnel. Meanwhile, the VPN provider themselves, well, they can see your DNS queries and your destination IP. That is exactly why choosing a trusted provider with a strict no-logs policy is so vital. They handle the routing, but thanks to standard web encryption like HTTPS, they still can't read your passwords or private messages. And finally, that destination server only sees the VPN's IP address, keeping your actual physical location completely hidden.
Section 4. Under the hood. Let's look at the OSI technical architecture.
As we zoom in on what's running in the background here, we have to ask a pretty big question. We know the tunnel is encrypted, but what exactly is happening under the hood to actually make this connection secure? To really get it, we need to look at the cryptographic handshake.
This process relies on a brilliant hybrid encryption model, like the kind used in SSL and TLS. It goes down in two main stages. First up, asymmetric cryptography verifies identities. Think of it like flashing a highly secure ID badge before someone hands you a lockbox. Once those identities are verified, both sides agree on a random, shared session key. This key uses symmetric encryption, which is incredibly fast and efficient, locking down all the actual data transmission for the rest of your session.
Section 5. Comparing security layers across network protocols.
Now that we know how that secure handshake worked, let's compare how different protocols apply these protections. HTTPS operates up at the application layer, that's layer 7. It's awesome for protecting your web passwords, but it's limited just to web browser traffic, and it definitely doesn't hide your IP address. A VPN, on the other hand, operates much deeper, down at the network layer, or layer 3. Because it sits lower in the stack, it acts like a giant blanket, wrapping all of your device's traffic inside that encrypted tunnel. We're talking background apps, system updates, DNS queries, the whole shebang, while simultaneously masking your IP address.
To actually build that layer 3 tunnel, networks rely on specific VPN protocols. WireGuard is kind of the modern darling right now. It's incredibly fast, super lightweight at around just 4,000 lines of code, and uses state-of-the-art cryptography. Contrast that with IPsec, which is your traditional enterprise heavyweight. IPsec is incredibly robust and supports hardware offloading on massive corporate firewalls, but it's also incredibly complex, packing tens of thousands of lines of code. Then, of course, you've got OpenVPN, a bit older but highly configurable and rock-solid reliable.
Beyond just picking a protocol, network engineers also have to figure out how traffic actually flows through the VPN. They usually choose between full tunneling and split tunneling. Full tunneling routes literally every single packet through the corporate network. It's highly secure, making it great for heavily regulated industries, but man, it can cause high latency and slow things down. Split tunneling, though, that only routes specific, sensitive corporate traffic through the VPN, letting everything else, like your normal web browsing, go straight to the open internet. It cuts down latency and is pretty much a perfect fit for modern cloud-based workforces.
Finally, Section 6. When to actually use a VPN in practical scenarios.
All right, bringing this all back to reality. When is a VPN actually a game changer, and when is it just overkill? If your only goal is to stop your ISP from logging your DNS queries and building a weird profile on your habits, you don't necessarily need a full VPN. You can just use encrypted DNS, like DNS over HTTPS. It secures your queries without bottlenecking your speed, but you absolutely need a VPN if you want to mask your real IP address to access geo-restricted content, bypass strict network censorship, or, and this is absolutely crucial, if you're sitting at a coffee shop on public Wi-Fi and need to protect your entire device from local network spoofing.
It's also worth pointing out where the industry is heading right now. In the corporate world of 2026, the traditional full-tunnel VPN we've been talking about is rapidly being replaced by something called Zero Trust Network Access, or ZTNA. Instead of giving a user broad access to the entire corporate network, which is super risky if their device gets compromised, ZTNA grants authenticated access only to specific individual applications. It is a massive shift in how enterprise security is structured. Ultimately, relying on just one single tool isn't going to cut it anymore. True digital privacy and security today requires a defense-in-depth strategy. It's all about combining encrypted DNS, secure HTTPS protocols, and robust VPNs at the network layer to make sure there are zero weak links in your chain. So, as we wrap up this explainer, I want you to ask yourself, knowing what you know now about exactly how your data travels, is your current setup leaving you exposed?